Hey, this is MJ, call sign KW3KW, and welcome to another episode of Ham Radio Made Simple. Today's video is focused on solar weather and its impact for ham radio operators. What's the impact and the difference between a CME, a solar flare, corona holes? Today, I'm going to break that all down so that when you look at the solar weather, you're going to say, okay, a KP index of 5, I know what that means. So if you're really interested in how to operate under bad solar conditions, then you're going to need to watch this video. And I appreciate all of those who are trying to help others find this channel by hitting the like and the subscribe button, and so that they can come across this material a little bit easier. And thanks for all the great comments and your continued prayers for my neurohealth condition. Today, I'm going to go over solar weather. Why is it important? The difference between a solar flare and a CME and its impact, solar winds, the Earth magnetic field, solar cycles, the impact of a weakening magnetic field, which we are now in. And at the summary, I'm going to, again, summarize everything about solar weather, but more importantly, how to operate ham radio during the solar storms. So when we look at solar weather, it has a direct impact on ham radio on the HF bands. There's a positive side of it. Like, for example, during the solar maximum, there are more sunspots that can then ionize the atmosphere and give better propagations, especially for the 10, 12, 15, and 17 meter bands. The negative side of it is going to cause CMEs and solar flares. It's going to have cause geomagnetic storms impacting the HF bands. And as the time of recording of this, early June of 2025, we've just been hit with geomagnetic storms for 4 or 5 days. And so maybe this will resonate with you if you were watching this right after that. But if not, understand geomagnetic storms will impact your outcome when you're trying to use ham radio. Now, during the solar minimum, there's less sunspots, and so the 10, 12, 15, and 17 meter bands can become nearly unusable. So since we're in the peak of solar cycle 25, I suggest that you try using those bands now, because in a few years, they may not be workable too much. Now, solar storms are becoming more frequent, and what are happening is there's more radio blackouts, and there's frequent unusable bands, and I'll explain why that happens. But first, let's look at the composition of the sun. It's the fourth state of matter, plasma, solid, liquid state. Plasma is the fourth state of matter. It has super hot ionized gases, and as the sun moves, it's generating a magnetic field, and that's the key part. A magnetic field, both the sun's magnetic field and the Earth's magnetic fields, they impact each other. And as solar winds are basically escaping from the sun's gravity, we're always having solar winds. It's a question of how bad are the solar winds, and at what level do the solar winds become problematic for a ham radio operator? Now, sunspots, what are those? Those are actually colder, cooler spots of plasma caused by stronger magnetic fields. So as these magnetic fields build up, and all of a sudden then they release and then rush toward the Earth, toward our magnetic field, and can cause major problems. Now, when we look at the sun's output, there's always continually emitting solar winds. However, when you get a CME and solar flare or corona hole, the solar winds will increase significantly. The sun's always emitting like different types of wave, UV light, visible light, X-rays, but the things to focus on are the particles, the protons and electrons, and especially the electrons when they break away. So if you can walk away with this, understand the magnetic fields exchange particles between the sun's magnetic field and the Earth's magnetic field. Hopefully this makes sense. Now, there are conditions in space, not just on our sun. They come from the entire solar system, from an exploding supernova that actually comes into our solar system and into headed toward the Earth. But we're going to focus more on the sun, since it's the closest to us. That's our star. Now, solar flares can occur at the same time as a CME. And what is a solar flare? It's a burst of high energy particles near sunspots, not necessarily emitting from a sunspot, but near sunspots. And it's flung into space like a whip. And I'll show you a picture of that here in just a second. And this is the one that takes 8 minutes to Earth. And this is the one that causes instant radio blackouts, depending on Earth facing and where it's going and the intensity of it. And this is the one, if it's high enough X-class flare, like the Carrington event, it could fry your equipment. And so I've had someone ask me, what's more dangerous, a CME or a solar flare? And the answer is they're both dangerous, but I'd be more concerned about the solar flare torching, burning up my equipment as it throws all of that charged particles down my antenna line and up into my radio. So that's the one to be more concerned about, but you have 8 minutes to react to it if once you know that it's coming. Now, a CME is different. It's a coronal mass ejection. So it's basically just think of like a volcano of outburst of plasma blowing up and blowing out the sides. And this is ones that you're going to see more of the geomagnetic storms is the CMEs. The solar flares are not as frequent as CMEs, but they are explosive, but different. Again, I'll show you a picture here in a second. And the third component of the things you have to worry about are solar winds, and that's basically charged particles. It's a radiation storm in essence. And I'm going to break down all of these more. That's just a high-level overview. So if we look at a solar flare, you have plasma so hot that the sun's gravity can't hold it anymore, and it's hurled into space. So you're looking at here, this is like a whip-like action. If you see this is a solar flare in here. And again, it's an explosive burst of energy. It's made up of light and radiation, basically X-rays. And again, it takes 8 minutes to get to the Earth, and it drives the energy toward the poles of the Earth. I'll show you that in a second. A lot of times, very powerful solar flares will produce a CME at the same time, but a CME doesn't necessarily produce a solar flare. So if we look at the solar flare classifications in here, ranking of the power classes is also within 1 to 9. So if we look at B here at the bottom, that's the weakest. C, and these are actually good for ham radio. When you get these out there, the atmosphere becomes ionized, and you get really good results. M flares can be good as long as they're not direct Earth facing, but on more the side, again, good effects. But when you start to get into the X-class flares, this is the one that's most dangerous. And again, I'll break down when an X-class flare is most dangerous, because I could have an X10 and an X1, and the X1 could be more dangerous than the X10. And you're saying, how is that possible? I'll explain here in a little bit. The largest recorded, not estimated, largest recorded has been an X28 flare. So when we look at the solar flare, time matters in here. So the class of the flare is not as the most important factor. So let's say here's a solar flare you got right in here. And this one's a little bit longer duration, but this is a longer duration. This is the one you're going to be more concerned about is the length of the time of the flare. Okay, so a short is weaker, medium is stronger. And that's, so for example, here you're going to look here. That's a short duration. The longer, more dangerous ones, you can have like an M5 long versus an X1 short, and the M5 could actually be more harmful in here. But this is what a longer duration looks like. So when you're looking at the solar X-ray flux charts, pay particular attention to the distance in this. Okay, short, maybe medium, long. I'm going to be really concerned about this one. Just as duration matters, direction matters. And the question is it Earth facing? And how do you know? Well, first you have to understand where the Earth is in relationship to the sun. We're in the southern hemisphere, probably somewhere around here, and we're probably about this size of the sunspot over here. So anything that is in this area, I would say, actually I can go up here a little bit more. Like in this area, I call it is the danger zone. The more it goes toward the edges, the less impact it's going to have. So you could get a solar flare, a CME facing that could be a direct hit or a mid hit, but sometimes as it moves toward to the peripheries, you're going to get either a glancing blow or a miss. Now, be aware if this, let's say, was an M5, you're going to get a miss on it. But if it's located over here and it happens to be like an X12, you're still going to get an impact, even though it's not technically Earth facing. So when you get a solar flare, the first thing that happens is going to be initial burst causing radio blackouts. Secondary impact is going to be poor propagation conditions from minutes to hours, totally different than a CME. And so who's going to get impacted by it? The communication satellites in space are going to be damaged, could impact the power grid. And the most at risk are going to be the upper latitudes of Earth. So, for example, in 2003, Canada got hit by a strong CME and it knocked down their power grids for a period of time. But it didn't impact, for example, anything in the United States because they were more toward the poles. We were not. And so again, CMEs initially are going to have more impact in the upper latitudes unless it's a very intense X12 Earth facing, then it can impact everybody here. And like an X45, as I mentioned, went around the world. So can it damage ham radio equipment? Yep, if it's Earth facing and it's high enough X-class flare. The Carrington event in 1859 would be an example of something happened today. Picture us with all our electrical lines. Oh my goodness. It was estimated at an X45, and the telegraph lines literally had such intense electrical current going through it. It actually caused them to fail, caused the operators to get shocked, caused fires and burned the buildings down. And even those that still operated were workable. Without batteries, they were able to still transmit messages because the lines were electrically charged. Imagine all of that energy going through our electrical system today. If there's any way that you get an alert or warning about this, that's the time to really disconnect your antenna and disconnect your equipment from the wall. Now, a CME is a coronal mass ejection. It's a large expulsion of plasma and magnetic field from the sun's corona. So it looks like this. So look at a big cloud being pushed out from the sun versus a rope or whip action. And these are charged particles that move out in a large cloud formation. Now, the speed is going to tell you the intensity of the storm. If they say expected arrival in 15 hours, that's an intense storm. 18 to 20, less intense. But it does travel a lot slower than a solar flare, which is basically travels at the speed of light. So size matters. A minor blast CME is not going to have much impact as to a major. And again, is it Earth facing or not? And again, the difference, look at the cloud on a CME, look at a solar flare, you can see the rope whip type action. So what's the impact on the Earth? It's going to differ from a solar flare. This is the ones that you're really looking at, the geomagnetic storms that can cause longer disruptions. At the time of this recording, early June of 2025, for 4 days, we had solar storms just really bad up to G level 4. And it was very disruptive in here. Solar flare is not going to cause that long of a disruption. And this is what produces the auroras. And the worst kind is when you see a halo, or they talk about a halo CME, and if it's Earth facing, it's really bad. Now, if it's not Earth facing, you can still see one on the backside of the sun. And that energy can still come to Earth. But just to show you how powerful these can be, even on the backside of the sun, we can have some minor impact from it. So let's go over the difference between the two. So a CME is a cloud-like eruption. It has plasma and magnetic fields. It travels slower. These are the ones that produce longer-lasting geomagnetic storms for poor band conditions. Whereas the solar flares are sudden. They can actually, they look like a rope whip type of effect. They travel at the speed of light, and they can cause initial blackouts and minor geomagnetic storms from minutes to hours. However, also understand the higher latitudes are at greater risk and greater impact from a solar flare. And satellites will be the first to fail before damage to the power grid. So before the power grid goes down, the satellites are going to go down first. The best tool out there that they're using to measure geomagnetic activity within the Earth's magnetic field is the KP index. And it goes from a scale of 1 to 9, 1 being the quietest, 9 being the highest. Anything really like 4 or less is good for band conditions that you see in here. Once you start getting a 5+ on, you get into a geomagnetic storm, and they're ranked. So G1, G2, G3, G4, G5, like F1 through F5 tornadoes. It just gets worse as it goes up. So if you want to know whether or not you're in a geomagnetic storm, look at the KP index, because this is what the alerts are based off of, is the KP index. Now, when it comes to solar winds, there are always solar winds being emitted from the sun, and it's ionized plasma. It's always going on. And it's made up of protons, electrons, and magnetic fields are embedded into it. And again, I think you're kind of seeing this whole concept of how magnetic fields are an important part of space and space weather itself. And they easily conducts electricity, and that can be a problem. So when it hits our magnetic field, most of it's deflected, but it will travel along the magnetic fields toward the poles. So you can actually see, so this would be the backside, and this is the forward side. and this is the pressure that is being put on the Earth continually, is the solar winds. That's the pressure on the Earth. And so it's gonna hit the field, the magnetic fields get pushed to the poles going in here, and this is what it looks like on the backside of the Earth. Now, it causes auroras when it mixes with the gases in here, and that's what the auroras look like. And as I mentioned earlier, Jupiter, for example, has magnetic field, and it has its own auroras that happen at the poles also. So when you look at corona holes, they produce high-speed solar winds, and it escapes from the corona holes. So these are open areas on the sun that people believe were created with a dying sunspot, old sunspots in here. But they're considered unipolar in nature, which means they don't have magnetic fields extending into space and they're not looping back. And they're more common actually during the solar minimum. But if you look at this one, this corona hole, again, the southern hemisphere in here, it would be worse if it was here, but it's still Earth facing, but the danger zone would be more in this area. And again, I mentioned that they're formed from sunspots that are fading away. Now, this is what generates high-speed solar wind streams and causes geomagnetic storms in itself. So again, think of the solar winds as one of the three areas that causes geomagnetic storms. You've got a solar flare, CMEs, and solar winds are the three things that cause it, and they can all happen at the same time and make a geomagnetic storm even worse. But with solar winds, the speed does matter. And the Earth, if you can see in here, is a picture of the Earth and the sun. It's always shooting and deflecting around it the solar winds as much as possible. The normal speed is about 190 miles per second or 300 kilometers per second. So typically, when you get about 600 or 1,000 kilometers per second, you're in a CME event. So the winds increase significantly, putting more pressure on the Earth's magnetic field. So this is what we get the geomagnetic storms is because it's compressing the magnetic field on the Earth. And this is the result of that is the HF bands will degrade. You're in a geomagnetic storm, and the transmission and receiving of signals on the HF bands becomes much more difficult. It's also known that it can be burnout transformer stations and impact satellites, the solar winds. But it does have a positive side. It does protect the Earth from high energy particles outside the solar system, not just within our own. The solar winds are always pushing outward, and what it does, it creates the heliosphere. So the heliosphere right in here is this big thing around it, and that's because of the solar winds blasting outward. And it is, again, it creates a protective barrier from deep in space. And it stops interstellar radiation. Now, when we talk about plasma speed, that's the speed of the solar winds. Just like we talked about the KP index measuring geomagnetic activity to measure solar storms, where there is something that's, and if you look here, for example, it's the indicator of how fast the solar winds are traveling, and it's kilometers per second. So normal is 600 to 700, which you would see like somewhere right in here. That's normal. When you start to get above 800, that's elevated. When you get 900 and above, like we had recently, that becomes dangerous. So speed of the solar winds and density of the solar winds will have a greater impact. So let's talk about density. So the density of the solar winds is the indicator of the number of charged particles per unit of volume within the winds itself. And so when you look at here, this is the speed and this is the density. You could have high speeds and it won't be as much impact unless the density is really high, or high density and slightly slower winds. So it's really the two of them are going to determine the impact it's going to have and cause geomagnetic storms. So the range is from 3 to 10 cubic particles per centimeter in here. So the average is around 4, elevated is 5 to 7 cubic centimeters, and the danger is 8 to 10 when you're looking at it. So notice in here, this is getting up high up in here. This is really bad, but notice that the speed is dropping down. If this was way up here at the same time, then it would even cause a greater solar storm. So in summary of the solar winds, let's just kind of go over it. It's the third one that causes geomagnetic storms along with solar flares and CMEs. And their corona holes is the key source of solar winds. And again, it's made up of protons, electrons. Think of it as plasma ejections. Speed and density determine potential impact damage, not one or just the other alone. And the magnetic fields protect us and it shields most of it. And the energy is then diverted to go into the poles, causing the auroras. And the greater the storm, the greater the auroras move toward the equator. And this is going to be important when I discuss magnetic fields here in a couple slides. So when we talk about Earth's defensive shield, it's our magnetic field. And that's generated by the Earth's core, known as the geodynamo process. Through the Earth's rotation, it's generating electricity and it creates what is known as the magnetosphere. And this extends into space in closed loops. Now, the energy, a lot of it is directed along the path of the magnetic field toward the north and south pole. It is not really a due north. It wanders. Right now, it's less than 10 degrees from due north geographically. And again, it travels in closed loops, both the front and back side of the Earth. So our magnetosphere here is a protective shield. It protects us from solar winds, and this would erode Earth's atmosphere if we didn't have our magnetosphere. It would remove the air we breathe. And so no life on any planet can exist without some kind of magnetosphere in operation. When you have a CME, it stops the particle radiation from reaching the Earth, as well as solar and cosmic radiation. This is an example of what it would look like in a normal function. It has its tail, but as the solar winds and CMEs, it can compress, as you saw in the last video. So it's not static. It moves back and forth based on the pressure pushed up against it. So let's look at solar cycles. We're in solar cycle 25, and it's 11-year cycle impacts HF bands. And so right now we're in July, let's say July of 25. We're probably somewhere around here on the downward side. We already peaked here earlier in the year. So there's two parts. There's a solar maximum and there's a solar minimum. And this is the solar maximum, obviously, is a higher activity of ionization in the atmosphere. And this is really good for radio waves. The solar minimum, as I mentioned earlier, is not good, especially on the 10 through 17 meter bands. During this part, it may not even be workable whatsoever. So again, we're on the upside of it. This is a great time to use it. So in summary on solar cycles, we're in solar cycle 25. And remember, it's 11-year cycle. And the top half of the curve is the solar maximum, and that has a lot of activity, both good in the sense that the higher HF bands, 10 through 17, you're getting greater skip zones and they're open and you're really doing good contacts. I call that the golden age of the cycle. However, you're going to get more frequent geomagnetic storms. And you tend to get higher X-class flares after the peak on the backside right in here. You're going to be looking for more X-class flares in the next couple of years. Remember, the solar minimum is the opposite. It's harder to work the bands, the higher bands at the bottom part right in here, because there's less activity on the sun. And remember, when you're looking at sunspots, look at that magnetic complexity. The more they intertwine the positive and negative together, the greater the chance and the risk of explosive events to happen. And also pay attention to, is it Earth facing? And in particular, is it in the sun's southern hemisphere as well as Earth facing? These are the most important factors that you need to watch when you're looking through these solar cycles. Now, I'm going to bring to your attention something I think that is happening, and it's called a weakening of the magnetic field. And there's an excursion event that happens every 6,000 years with a magnetic pulse flip. And it's an exponential curve toward the end. So it accelerates every few years. So it's not like, we're going to do 1%, 1% over the next 100 years like that. What ends up happening, it could be 5% the first year, 10% the second year, 20% the third year, 40% the fourth year. And you see what I get. It goes exponentially. So as we just beginning this weakening part of the magnetic field in the excursion type of event, it has some consequences that are out there. So with a weakening magnetic field, typical minor storms are going to become major storms. So if you look over here like a G0, something like here, I'll get a G4 event of what we think which should be nothing, it could end up being like a G1 or G2 storms. And I'll get more into that here in the next couple slides. So difficult band conditions are going to result because there'll be more geomagnetic storms. And this also is going to cause extreme weather changes because as more energy gets through the magnetic field and gets to our Earth, it's going to charge the weather and charge the storms. So again, there's a lot of papers that are coming out recently on this because of some events that have happened that have waken them up. So let's talk about what drew their attention. So if we look at the magnetic field in 2003, it was a Halloween storm. That's what it was called, and particularly in Canada. They were greatly affected by this. 486 and sunspot 484, and you can look over here, kind of breaks down all the different events that have happened. So in this storm in 2003, between October 19th and November 5th, there were 17 major flares. You can see a 5.5, a 17.2, a 10. And if you look over here on the graph, you can see there was another 8.3 right after it, a 4, and an X28 that was more not Earth facing, but on the periphery. A lot of activity, very powerful. It was the 6th and 16th largest storm since 1932. And it impacted Canada's power grid. Now, auroras should only go as far as south as California, Texas, and Florida, which it did, and said, okay, that was okay. We expected that. But what happened in last year, May of 2024, under the Gannon storm? Sunspot AR3364, which you can see over here, there was a high M class flare on the 8th, on the 9th, 2.2 and a 1.12, and an X class 4 on the 10th. So yes, we had a G5 magnetic storm, but the auroras went near the equator. This was not expected. We had to, again, look at the 2003 Halloween storm, and it only went, south of Florida and California. This went to near the equator. How could that happen? Because the magnetic field was weak and allowed all that energy to go down that far, because more energy came in and was not being filtered out. And as of June of 2025, this past week and a half, we've had a lot of solar activity, solar storms forecast by NOAA and NASA. We're like, G1, and we get a G4. It went as high as G4. So I'm watching them miss the forecast on these storm levels because they're under the paradigm that the magnetic field is still what it used to be years ago. It's not. As it weakens, we're going to get more and more storms coming through that should have been a low-class storm, and now are going to become more stronger storms. So let's jump over to the website so that I can show you where to look for information. So you can look at the KP index, you can look at the wind speeds, the density of the wind speeds, and other tools that will help you as you look at solar weather. If you're in ham radio, I do this every day because I want to know before I get on the air, am I going to be able to connect, or is it going to be a bad day? And so you don't sit there, maybe go out to the park and realize, why am I making no contacts? Well, you're in the middle of a geomagnetic storm. So let's jump in and show you how you can utilize and leverage some of the information by these great websites. There are 4 sites I go to look space weather now. And the first one is QRZ. And what I'm looking at, for example, over here is the HF band conditions, and it looks pretty poor. And it's telling you that the geomagnetic field is active. So this is a really good one to just to start out your day, because it's really focused on ham radio. The next one, you have Solar Ham that is out there. Excellent site to go in, and you can actually look at the last flares that have happening 2 days ago, yesterday, and today. And it'll show you whether it's a C class, M class, X class. And you can notice the time of duration of this. This is a longer duration. This is a shorter duration. So again, this is, remember what you want to look at, C, M, and we know if it gets into X, it's an issue. And the forecast today is for June 7th is a G1 storm. So you can go under the detailed forecast, and as of June 7th, it's showing you that at 2100 hours, you can expect something to happen. Now, are these 100% reliable? No, but they're better than nothing, and that's darn good for most of my experiences on it. So if I go look at Solar Ham, you can again go down the website, for example, and you can look at the KP index. Everything's below 5, so that looks good for as far as geomagnetic activity. And he does give a weather update, but today is the 7th. He hasn't updated it, and that's okay, because this is one guy trying to do this 365 days of the year. I don't know how he does it, but he gives a great summary forecast if you look down in here. And again, you can scroll through the sites. You can see where the sunspots are and the size of them. So again, you can play along with this one. It's really good. The next one is the homepage of NOAA. And this is telling us right now we're in a G1 minor storm that is happening. And again, you can play along with this. If you can click it on, it's going to actually tell you more information if you click on under the G1. It also has a lot of information that you can look up. The one that I really like to do is if you go under dashboards, And you can pick all of them, but I like Space Weather Enthusiast. And now I can look at the solar flare class. I can look at the solar proton flux and the KP index. These two I pay a lot of attention to, these two. I like to look at, and it tells you, breaks it down in more detail over here. So keep going down, you can actually get, you'll actually see if there's a solar flare, you can hit the play button, and you'll actually see it happen, especially if it's a halo effect. This is they call it the Enlil prediction. And for example, I can just click this on, and if I hit the play, this is trying to show you that if there was a CME, here is Earth that you can see, and this is what's happening to it. We're getting some activity. That's why you see the yellow happening in here. Green means it's okay, but it'll get red, and if it gets black, and it shows you exactly when you can expect it to hit the Earth. This is the one. It's more time predictive and intensity predictive as a great tool to look at. Next, I'll go to Space Weather News. This is a great one. He has a lot of videos. And again, he has a lot of the same material that are out there. Breaks everything down. And again, just 4 good sites to have fun and explore and try to look at the information on here. So again, like I said, he can actually even show it in here. Bottom line is, there's so much behind each of these. I don't have the time to go into it, but I showed you the key parts to where to go into it. Just explore with it, have fun, and post any of your comments. If you know of any other sites that are as good, I would love to know and add it to my collection of bookmarks. So thank you, and let's get back and wrap this up. Okay, let's wrap this up here. 2 pages on the final summary here. In the 11-year solar cycle, toward the top of the peak is the solar maximum. That's when there's best activity for ham radio. Solar minimum is low activity for ham radio. When we're considering a CME, a solar flare, corona holes, is it Earth facing? And we know now that on the sun's southern region is the worst. If it's Earth facing toward us, is going to have the greatest impact. Now, solar flares can't trigger a CME, but they're fast to Earth, 8 minutes at speed of light. Size and duration matters, as we talked about. It could be a high-class flare, but if it's low in duration, it may not have much of an impact. The greater the duration and the size, the greater the impact. Blackouts are caused by these and possible equipment damage. CMEs are much longer to get to Earth, 15 to 18 hours. They produce more what I call the solar storms that can take, half a day to a couple days at a time, make the bands unworkable. Also, they're classified from G1, the lowest, to G5 is the highest storm. Solar winds are created by the corona holes. And again, if it's south facing in the sun toward us, that's the worst. They do cause solar storms. And be aware of the ongoing weakening of the Earth's magnetic field, because minor storms are now becoming major storms. So as a ham radio operator, how do I deal with these situations? What's the best practice? In the digital world, like JS8, FL-Digi, you're going to have to use slower speeds when you're doing it. That can make the difference in getting the message across. It's not fun, but when you're in a solar storm condition, you make sure you do that. Make sure your ALC is spot on where you want it. Your sound mic is absolutely good, that you're having it. If you're using JS8, your time delta is minimal. Those are all things that are going to make the difference whether you can send a message and have it decoded. You could use like relay options. I found, like, for example, when I'm working with my friend Rick, KC1 PHY up in Massachusetts, he can hear more people than me. So I will hit him on JS8 and hit the hearing option. And then I can relay messages through Rick to other people going on. So you're going to probably end up using the relay option more. On the voice side, expect fading and increase in noise. That's going to happen. So you may have to use headphones. Make sure you know how to use your filters and use them. And learn best voice settings for your rig. You don't necessarily go with the default settings. There are some great smart people out there who have your rig, your model, and have figured out how to get the best sound out of it and how to best utilize the filters on it. So that's stuff that you're now going to have to step up in your skill sets and know how to use your equipment better. So hopefully this has been helpful for you too. So this is MJ, call sign KW3KW with Ham Radio Made Simple. Thanking you for watching this video, and I hope it helps you become a better ham radio operator and know the conditions you're working in. So if you found value, please hit the like, the subscribe, and thank you for your great comments. So this is MJ, KW3KW, out.